So today we're doing chapter 13, dates and times. I think one of the things I like doing whenever I go through chapters in this book is just try to maybe take a step back itself and kind of try to think through what exactly the entire journey has been so far. So the entire idea of the book breaks down data analysis into 4 different parts. It starts with like visualization, then goes over to wrangling, then ends up with like modeling. Then goes to programming, then ends up with modeling itself. And the part where we currently are is wrangling. And the major idea of wrangling is just trying to understand toolkits that can allow you further prepare your data in a way that can easily be modelable and can also be visualized. So one of the things that the book is very big on teaching is, data cleanup itself. And I guess that's what the entire Wrangle category is trying to teach. Now, under Wrangle, that's where we end up at under date and time. And the package we are going to be working with is called Lubridate, right? So I decided to do a quick note here. The entire chapter covers 4 major parts. So the first part is, how do you create date and times, right? So how do I create my own dates? Second part is date and time components. How do I extract from existing date and time structures? The third part talks about time spans, right? So after I have created my date and times, or if I have existing date and time components, how do I calculate with them? Like, how do I do arithmetic with them? Then the fourth part talks about time zones, right? So like, how do I deal with, let's say, respective time zone in different geographical location and things like that, right? So we'll be going through each of those parts itself, or each of those categories themselves. So for a bit of introduction, I think this part is very interesting for me. So it says that the chapter will show you how to work with date and time. So like I said, both creating, working with existing date and time structures, or trying to do arithmetic with them. But at first glance, you could think that dates and times could be simple. But as you kind of go on, you kind of realize that they're actually more complicated than you think they are, right? And just to get the sense, they decided to ask 3 major questions. One, does every year have 365 days, right? So the answer is no. But I guess the interesting thing is years that have 366 days happen every 4 years, things like that. So if you're looking at, let's say, a data set that has a 10-year span, for example, it means you probably have some of them that would have 365 days, some that would have 366 days, right? The other 2 questions says, does every day have 24 hours? Interestingly not. I think when I was reading through this part, there are actually some days that have 23, some days have 25 hours. Then does every minute have 60 seconds? Also interestingly not, right? So it goes on to say, I'm sure you know that not every year has 365 days, right? So we know how to determine a leap year. So you might have remembered that many parts of the world use a DST, a daylight savings time. So some days have 23 days, some days have 25 hours rather, 23 hours, 25 hours. You might not have known that some minutes have 61 seconds. I had no idea about this because every now and then leap seconds are added because the Earth's rotation is gradually slowing down. So I think one of the things the chapter is also trying to teach is things can actually be a bit complicated if you decide that you want to get into the technicality itself. So that's why it ended by saying, this chapter won't teach you every last detail about date and times, but to give you a solid grounding of practical skills that would help you with like common data analysis itself. Right. So I would like to start from there. Maybe the other bits before we go into like the meat of the entire chapter itself is we'll be working with the Lubridate package, which makes it easier to work with dates and times in R. Now, this Lubridate package is not part of the core tidyverse package. because you're only going to need it when you're working with date and times. So throughout the entire chapter, we're going to be working with this lubridate package itself, right? And we're going to use a particular data set called NYC Flight 13 data set. So this is a data set that you would have to install, similar to how you're installing your lubridate package. So you have to run library NYC Flight 13 to get access to this data itself. So I think one thing on this data and also one thing on this chapter is I think is useful for data sets that has anything to do with, let's say, any concept of a date or a time. So like if you're working with a data set that doesn't just touch on, let's say, a year, but maybe touches on like a particular time within a particular day or a particular hour between a particular period or things like that, right? And you see that play out in this data set itself, because the entire idea, I mean, without even looking at like going through the data set, the entire idea of like a flight's data set would be, departure time, arrival time, and things like that. And that's where the entire analysis work of, let's say, an aeroplane operations company is probably going to be working on, right? So the first bit of this chapter is on creating dates and times, right? And so it starts by saying there are three types of date or time data that refer to an instant in time, right? You have a date, you have a time, and you have a date time, right? So a date, tables print this as dates. So we've talked about tables in the past. They're like data structures themselves, similar to how you think through every other kind of data structure you could probably have. They print this as dates in this format. Time within a day, tables print this as time. Date time is a date plus a time. It uniquely identifies an instant in time, typically to the nearest second, right? So tables prints this as DTTM. Elsewhere in R, if you're working with base R, you probably see POSIX CT. But I guess I also agree with this. It's actually not a very useful name because it's very, very confusing. Like I also do not understand what this means.
Yeah, I mean, I was trying to figure it out as well, and I cannot think of anything.
Yeah, so I guess that's why it's good to work with like the tables data structure itself, because it just prints this into date and time itself, and I guess that's a lot more useful, right? So in this chapter, we are going to be working with dates and date time. As R doesn't have a native class for storing time itself, and if you need one, you can touch on the HMS package, right? So we'll talk about this as I go on in the chapter itself, right? So I also decided to flag this. You should always use the simplest possible data type that works for your needs. That means if you can use a date instead of a date time, you should. Date times are substantially more complicated because of the need to handle time zones, right? Which we'll come back to at the end of the chapter. So like I said, there are four major parts that this entire book tries to touch. The final bit is this time zone, which we will touch on at the much later part in the chapter itself. Right, so how do we create dates and time, right? So the first thing is if you just want to see what is the date as of today without creating anything, you could just use the argument today. From your bracket, close your bracket, you get what date is as of today. Or you could use now. It just gives an extension of the actual time itself and a time zone, right? And as I get towards the later part of the chapter, you notice that this is based on your system configuration itself. So depending on the particular time zone where you are, that's what this is going to actually spit out, right?
So it doesn't have to do anything with R, it has to do with your system. It doesn't access the internet or anything. Exactly.
Otherwise, there are three ways you can actually create date and time, right? So you can create it from a string, you can create it from individual date time components, or you can create it from an existing data time object, right? So let's start with creating date time from strings, right? So most often than not, you will get your datetime data as strings. We've talked about strings in the past. I think one of the chapters that one of the cohort members took us through. Was around strings itself. But another approach is can be provided by the Lubridate package itself, right? And I think when we get into this, pretty clear. It's a bit more simple. They automatically work out the format once you specify the order of the component. So I guess this part is very important, right? So as soon as you specify the order of the component itself, they are going to help you work out the entire format, right? So to use them, you identify the order in which the year, month, and day appears in your dates. You arrange them using Y, M, and D, right, in the same order. Then that gives you the name of the Lubridate function that you pass your data, your dates through. So an example is YMD. You notice that the year comes first, the month is second, and the date, similar to how you're doing it here. If you're doing MDY, you notice that your month comes first, your date comes second, and your year comes last. If you're doing DMY, you notice that your day comes first, your month comes second, and your year comes last, right? So again, if you specify the order of the component itself, you can actually get this result itself, right? So the other interesting thing is these functions also take unquoted numbers, so you don't actually have to quote them, right? This is the most concise way to create a system datetime object, right? So you can actually just use YMD, the year, the month, and the day, right? And it actually give you this, similar to what you got here, right? So it also goes further to say YMD and and his associates or friends also create dates. If you want to create date time, you can add an underscore and let's say one more of the hour, minutes, or seconds to the name of the passing function, right? So YMD underscore HMS. You can see the year, which is the Y, the 1, which is the month, 31st, which is the day. Then I specify 20 hours, 11 minutes, 59 seconds, right? So it's going to spit that out here, right? It's based, like the basic UTC. Again, when we get to time zones, you see why this is important. And I'll touch on that when we actually get to time zone itself. But right now, if you do this, it's going to spit this out under UTC, right? You can also force the creation of a date time from a date by supplying a particular time zone, right? So I can decide to actually force this entire structure by conforming it to a particular time zone that I want it to fit in. So in this case, all you just do is you use YMD, you put the year, the month, and the date, again, following this order, and you can just put the time zone. So TZ equals to UTC or PDT or whatever other time zone you want to work with, right? So that's one way of creating date time. The second way is from individual components, right? So instead of a single string, sometimes you're going to have your date time spread across multiple columns. So this is usually going to be how you probably receive a data set itself. And the question now becomes, so what do you do when you receive that kind of data set? So if you go back to the NYC flight 13 data and you kind of spread that out, it has 336,000 thereabouts rows and 5 columns, right? That's if I select just this, actually, to give me a table of 376,000 rows and just 5 columns. The 5 columns are going to be the year, the month, the day, hour, and the minute. Now, if I want to create a date time from this kind of input or from this kind of table, what I'll now use is a make date function for dates or make date time function for date times, right? So similar to how I created this entire argument. So flight, I pass this through for it to only select 5 columns, right? So what you do there is, so instead of ending the argument here, you continue it by passing it through a mutate function. And I decided to put this definition of this mutate function because it's one of the other wrangling tools that we've touched on in the past. So this would mean a mutate function. In a tidyverse package, it is used to create or modify a particular column in a data set. So everything you're trying to do here is either to create a column or to modify a particular column itself. In this case, you're trying to create a column. And the column you are trying to create is, you want the column to combine all this together, right? Which is why they're using make date time. You put your year, you put your month, you put your day, hour, minutes. And again, these are types of colons that you have selected from this function itself, right? Then your result is now going to be an extra colon, again called datetime. Like we said, this is how the lubricate package spits out a date time colon in as a table, right? Then you now get like a combined set itself, right? So now I have the year, the month, and all it does is it combines this entire information for me, right? That's what this make date time will do. So let's stretch this argument a bit further. So let's do the same thing for each of the 4 time colons in flights. The times are represented in a slightly odd format. So we decided to use the modulus arithmetic to pull out the hour or minute component. So I'll explain what this means. So similar to what I just did here, flight select, I selected a number of colons. I passed it through mutate function. I created a colon itself that combines all this together. That's what this is now trying to express, right? So the first thing is I decided to create my own argument or my own function itself called make underscore datetime underscore 100. And I'm going to pass it through the flight data itself. So I created my own function. So it started from function. I put a number of colons, and it tells what I needed to do is for particular colons, I want to create a modulus by dividing it by 100 for the time data. Then what I'm going to get is now I can now pass this function, this make datetime underscore 100 function, to now create certain new colons, right? So again, my flights data. So now I have a new vector, my flights underscore dt, right? I'm assigning it from the flights data. I'm filtering out particular departure times that are not available, and also filtering out particular arrival times that are not available. And I'm passing this through a mutate function. And what I needed to do is create particular colons called datetime. Or in this case, you're not creating a colon, you're modifying a colon because they already exist, which is, they're already here, so they already exist. But the way I want to modify it is, since I'm creating my own function, I want it to conform this time component itself and divide it by 100, right? So I have my year, I have my month, I have day, and now I'm creating or I'm modifying the colon itself to have departure time. I modify another one, similar function I created. I have my year, my month, my day, and I now have my arrival time. I do another one on scheduled departure time, pass it through the same function, year, Monday, modify this, then scheduled arrival time, year, Monday, and modify this, scheduled arrival time, right? Then I now decide to select from this entire argument itself, I only want to see particular colons. So I want to see the origin colon, destination colon. I want to see colons that end with delay and colons that end with time, right? So this is what is now going to give you, right? So origin, destination, a delay, arrival, departure time, right? So I mean, all these are just mechanics or walking through R itself, just trying to create a function. But the major part of what it's trying to teach us is how to use this make date time function itself, right? So I can create my own arguments or my own function in this case, and try to use it to wrangle my entire data to either create or modify certain colons in case I want to see certain things. And right now, if I decide to express the entire data set, the new data set I just created, so flights underscore dt, I get a table that has a reduced number of colons, reduced number of rows, now 9 colons based on everything I wanted to see here, right? But the interesting thing now is now the visualization, right? So this allows me to do some interesting things. An example is with this data, I can actually visualize the distribution of departure times across the year, right? So again, just takes us back to our ggplot package. I pass this by this new information that I've created, this new data set I've created. I pass it through ggplot. Yes, I want to see the departure time, right, on my x-axis. Then I want it to give me frequency polling. bin width of 86,400, and like they gave us a comment here that this just means a day. So what I'm trying to see is individual days across an entire year itself, right? So from January 2013, January 2014, right? And I can see what the departure time kind of looks like, right? So you notice that in times when departure time is very low, especially at the beginning of the year, for example, right? So in January and maybe sometime in, this should probably be like February, thereabout, or late January, right? But if you want to be a bit more granular, I can also see it within a single day. So the same thing, I passed the new data set I've created. I decided to filter out departure times, again, see how I created my date in this case. So YMD, I'm asking it for 2013 January, 2nd of January, right? So I want to see what happened within that particular day, within this particular day itself. I'm filtering out anything less than this, right? So in this case, departure time on my x-axis, I create a bin width of 600. Again, 600 in this case means 10 minutes. And I guess you can play with the bin width as much as you want. I mean, it depends on the level of granularity you're looking for in your data. But in this case, based on everything I've created so far, so like how I've created my date and my time, I can now see a certain set of information. An example would be towards the back end of like when the day was ending in January 1st, you notice that there's a lot less departure time. Maybe there's a lot less flights, depending on what the information looks like. But this trend line definitely has a negative slope at this stage, right? Then you notice that, at the beginning of the year itself, a lot of early flights that happen. So from, let's say, like 4 a.m. in the morning all the way up to like noon itself. Then noon steadies out, increases slightly in between before early evening, then decreases as the day ends itself. So I can only see this level of granularity because I've been able to create date and time itself that can allow me be a bit more detailed compared to the initial flights that I was at the very beginning, like how this was. Now I can create a bit more granularity in the information. And the only way I can do that is because now I have a function that allows me to create date and time, right? So I've run through this, right? So how else can I create date and time? I can also do from other types, right? So again, you may decide to switch between a date time or a date, right? Now this is now the function of asdatetime or asdate, right? So an example is, remember how I said you can actually look at what the date looks like today. I can decide to do asdatetime today, and I get this, or I can decide to do asdate now, and I also get this. Right. Then I can go a bit more granular. Sometimes you get date times as numeric offsets from the Unix epoch 1970 01 01 01. If the offset is in seconds, you can use as date time. If it's in days, you can use as date. So an example would be this. Again, so I guess this piece of information is why in the introduction bits kind of mentioned that there's a lot of information that you might need if you want to work with datetime components, but maybe try to keep things as simple as possible. Right? I guess that's one of the major takeaways that I got from this chapter. Right? So I will try to do the exercise at the end because I think I've done this almost 40 seconds itself. So let me just run through the other components of chapter. So apart from creating dates and times, the other thing I can also do is how can I work with existing date and time structure, right? So that's what it meant by datetime components. So he said now you know how to get datetime data from ours that datetime data structures. Let's explore what you can do with them, right? So this section will focus on what they call accessor functions, right? That lets you get and set individual components, right? So the next session will show you how arithmetic works. So when I get to the third subsection of the chapter, then we'll talk about like how to do multiplication and addition and different kind of math functions on data types. But for right now, what we're trying to do is how do I extract information from an existing datetime structure, right? So let's start with getting components, right?
Sorry to interrupt you. Can I ask something? What exactly is an accessor function? Do you know? I've never seen that before.
So there are going to be functions like this. So like when I touch on them, it's going to be functions like this, like functions that allow you access particular information from, let's say, an existing datetime structure itself, right? So
right, okay. Mm-hmm.
Exactly. So let's say, I'm a very big Excel user, so that's usually where my first thought process used to go.
Yeah, me too.
Exactly. So if I have like an entire date function itself on Excel, I could use a year function, for example, to extract just what the year looks like. Those functions that allow you to extract are what they refer to as accessor functions.
Okay.
Yeah.
For the clarification, I have never seen that before.
Yeah. So an example here is if I create an object here called datetime, and let me see what note I kept here. So I put. Do you remember how this was created? So this was under like the section that we just finished. Like if I want to create a date and time itself. So this is an example of I want to create a date time that has a year, month, date, hour, minute, and seconds. That's why I passed this through. Remember how I said you don't have to put it in brackets. You can actually put them alone and you can actually spit it out. But now the interesting bit is now I've created this object with this function. Can I actually extract from this function? Now there are a number of ways you can extract. I could use year, which obviously gives me the year. The month gives me the month. The M day gives me the day itself. Y day gives me a year day. So it tries to calculate in terms of like number of days within that particular year. Then W day gives me number of weeks itself. Right. And I think it's kind of covered up here. Right. So M day gives me day of the month. Y day gives me day of the year. Rather, day of the year, not number of days. Then W day gives me day of the week. Right. So it also goes further by saying for month and day of the week, you can actually set the label to true, right, to return the abbreviated name of the month or day of the week, right? Or you can actually use false in case you want to use the full name itself, right? So you can add like an extra argument itself in this month or the day of the week itself by putting the label. Right. Let me actually highlight this because I think it's very useful. Then now, I guess this is another bit of where it gives you interesting data points to actually visualize. So now I can use the day of the week to see that there are actually more flights that depart during the week than on weekends. And you can see that play out on a Sunday and on a Saturday. And I can see that like from Monday to Friday is fairly constant. But after those days, there's just a lot less flights that happen on those days itself. And the reason why I can see this level of detail is because I have a function that allows me to extract information itself from the departure time, right? And in this case, we are setting it to true because we are trying to abbreviate this x-axis, right? So it tries to go into some interesting level of detail here. So he said there's an interesting pattern if we look at the average departure delay by minutes within the hour. Again, the way I'm going to be able to get this minutes is because I have a function that allows me to extract, right? It looks like flights leaving in minutes 20 to 30 and minutes 50 to 60 have much lower delays than the rest of the hours. So like you will see that in this deep when we get here, but let me just explain how we actually get this graph itself. So I pass my flights underscore DT data that I created. I try to mutate for a minute, right? So like create a column for me where I want to extract the minutes of the departure time, right? I want to group this by minutes itself, where I summarize that the average delay should be the mean of my arrival delay and remove any information that is not available, right? Then I pass this through ggplot, right, where I'm plotting my minutes on the x-axis, my average delay on the y-axis, then create it in a line function itself, right? And that's what this tries to represent, right? So everything we're just trying to benchmark the average delay, this formula that I just created, the mean of the arrival delay against the minute itself. So like you mentioned here, looks like flights leaving in minute 20 to 30 or minute 50 to 60 have much lower delays on average than the other minutes itself. And I guess that's what that's how it plays through in this information, right? So extra level of detail. Interestingly, if we look at the scheduled departure time, we actually don't see such strong pattern, right? So again, create this object, pass through flight DT information, mutate, create a colon called minutes, create minutes from the scheduled departure time, group it by minutes, then summarize, create an average function of the arrival delay, pass that through ggplot, put my scheduled delay on the x-axis, pass that to ggplot rather. This is the data I'm looking at, which is data that I just created up here, right? Put my minutes on the x-axis, put average delay on the y-axis, then create it in a line function, right? So you notice if you benchmark both, you actually won't see that kind of information itself, right? And one of the things that he tries to teach us here, I guess it's another bit of learning, is so why do you see the pattern with the actual departure times and we don't see the pattern with this? One of the things he's trying to teach is always be alert for this sort of pattern whenever you're working with data that involves human judgments. Why? Because there could be a strong bias towards flights leaving at nice departure time. So this could just be a data recording error itself, right? So like if you're working with data that I guess requires some level of human judgment or human input, just have that kind of sense that some things might not actually play out the way they are supposed to play out itself because of that human bias, right? So I guess that's just an extra bit of nugget. The other thing we can also do when we are trying to, let's say, extract or modify datetime components from like existing data sets is we can also do rounding, right? So an alternative approach to plotting individual components is to round the date to a unit of time, right? So you can actually use floor dates to round it down. You can use round dates, or you can use ceiling dates, right? So that's what they try to explain here. So each ceiling date function takes a vector of dates to adjust, right? And then does the following. Number one is to round down. So that's what the floor dates tries to do. Number two is to round up. That's what the ceiling date tries to do. Or you could round to. That's what this round dates tries to do. So an example would be my flight DT data set. I try to do a count in terms of week, right? Then I do my floor dates. I want it to round down my departure time in terms of weeks. I do a ggplot. I have week on my x-axis, the count itself, on my y-axis, and I pass it through a line, right? So all it just tries to do is just to summarize the information itself. So round down my departure time itself, or the week extracted information under my departure time itself. So I can see a bit more cleaner information, which is why this x-axis is a bit more cleaner information that is currently presented, right? Now, the final thing we can also do with accessor functions is now setting components, right? So I can also use the accessor functions that I mentioned earlier, the year, date, time, hour, things like that, to actually set a component of a datetime, right? So imagine I have a datetime object created from this function itself. I can also decide, so like this function created a date this would be 8th of July, 2016. But if I decide I want to set particular components, I can actually pass this accessor function year for datetime, and I want it to set it to 2020. So you notice that it changes to 8th of July, 2020. I can do the same thing for the month. I can also do the same thing for datetime, right? So
cool. So these functions are not just to retrieve information, but also to change components if you need to. It's very useful.
Exactly. Then interestingly, the other point is, so instead of going through, if you have a number of things that you want to change, instead of going through each of these steps, you can actually just use the update function itself, right? So I can just put this object that I created, right? I run it through the update function. I put the object, I put the year that I want to change it to, the month I want to change it to, the day of the day of that I want to change it to, and the hour. So you notice now it has changed from 8th of July 2016 up here, and it has now changed to 2nd of February 2020 because I've now force-fed this information, including the second hour, right? Then now, I guess the extra bit of information here is if these values are too big, right? So in the case where February has 28 days, and I'm trying to update it to go to like 30 days, it's going to roll over, right? So this kind of information here that I'm trying to change 1st of February, I want it to conform to 30 days. Since February doesn't have 30 days, it's going to move over to the 30th day from that 1st of February itself, which is going to be 2nd of March, right? And also if I also decide I want to update the hour itself, so I wanted to do 400 hours, moves it over to 16, all the way from, I think it started from 12, move it to 16. So that's like 4 hours difference, right? Then I guess extra information here. We can also use the update function itself in case I want to see some information. In this case, to see the distribution of flights across the course of a day for every day of the year, right? So I have my flights information. I pass my mutate to create a new column called departure hour. I want to update it to show. So again, I guess best way to before I go back to this is to see the x-axis here. All I'm trying to do here is to see information on January 1st itself. So from the beginning of January 1st to the end of January 1st. So what I'm going to do is I pass my departure time information. I want to see yesterday, right? So the only day I want to see in that yesterday, that departure time is just January 1st, right? And that's why I specified 1. And I wanted to update that one for me, right? I mean, this is a long way of doing this formation. I can equally just maybe select January 1st itself from that departure hour, right? Then I pass the departure hour column that I just created through my AES dataset, then create a bin width of 300, right? And now I can see this. And you notice that there's an interesting pattern. There isn't too many flights that happen early morning, and the flights also, reduce as the day closes itself, right? So let me just go to the third bit of this entire chapter itself, right? So we've talked about creating dates and times. We've talked about modifying dates and times. So the next part is now to work with time spans. So all this what this strategy teaches, can we actually do arithmetic with date and times, right? So can I add particular dates or subtract from particular dates or even in between particular dates itself, right? So he said next you would learn how arithmetic with dates work, including subtraction, addition, and division. Along the way, you'd also learn about 3 important classes that represent date times, right? So I guess the usefulness of these classes is to know 2 things. One would be what kind of arithmetic work can you do on particular types of date time information. Number 2 would be related to how the chapter was trying to preach. If you have a way to use a simpler data structure, just use it. And I think that's one of the things that these individual classes will try to teach, especially why periods might be better than using durations and what intervals try to do in terms of like a division itself, right? So if I start off with the class duration, right? If I subtract 2 dates, right? What I'm going to get is this, like just normally what I'm going to get is if I subtract today, the normal function today, from a function that I created, so YMD, I specify the year, the month, and the day. The answer I'm going to get is a number of days, right? So sometimes it could be useful, but most times, since this goes above, let's say, 365 days, it's difficult to actually interpret this number itself. What you can actually do and what the Libridate package allows you to do is to use a function called as.duration, right? So I can pass this object I just created, right, through as.duration, and it gives me the number of years, or at least the estimated number of years, right? And it's like 37 years itself, right? Now, the interesting bit is, so durations itself comes with a bunch of convenient constructors. similar to how we have accessor functions that allows us to extract. These functions are kind of allows us to construct information itself, right? So I have d seconds that allows me to construct 15 seconds. I have d minutes that allows me to construct 10 minutes, and it will give you your answer in terms of seconds itself. I think that's one of the things I didn't touch on. So it says the Lubridate package provides an alternative that always uses seconds, right? I have d hours as a constructor that gives me in terms of functions. So sorry, in terms of seconds, but also specifies in terms of the hours itself. Then I have d days, I have d weeks, I have d years. So you can use that as like to construct information itself, right? I will see how this is useful when we get to the arithmetic part. So it mentions duration always records the time span in seconds, like I just said. So larger units are created by converting minutes, hours, days, weeks, years to seconds at the standard rate of 60 seconds in 1 minute, 60 minutes in 1 hour, 24 hours in a day. So it's also useful to go back to the introduction in this chapter, where it's kind of mentioned that not all minutes actually have 60 seconds. I think that part is also quite important, and not all days actually have 24 days. So it depends on the assumption that you want to make for your underlying data itself, right? Now, one of the things that he also tries to teach is the flaw of this duration class itself, right? So the way he tries to explain it is, let me just do some quick arithmetics here. So again, I have a construction function, yeah, and I decide to just multiply 2 by this construction function, right? So the construction function is asking for just 1 year, specified in terms of seconds, the way Lubridate package will, but obviously 2 years. Multiply this by 2, I get 2 years, right? Then I can also add a day year plus a week plus hours, and it gives me 1.23 years, right? So that's one of the beauties of this duration class, right? And I can also do subtraction, and I can also add. So an example would be if I want to add 1 day to today, or 1 year to today, for example, right? Now, the problem here is now that the seconds that its duration class spits out, right? So it explains that because duration represents an exact number of seconds, sometimes you're going to get unexpected results. And I think this is a perfect case. So what it tries to represent here is, in case you have a full set of information here, you have the year, you have the time, and you have the time zone itself, right? And if I decide I want to visualize this, it's going to give me what I'm looking for, right? You know, similar to how I created this entire function, year, month, date, it's giving me what I'm looking for. However, if I add 1 day to this, everything changes, right? So it changes from 12th of March 2016 to 13th of March 2016, but it changes by 1 hour. No, it changes the time zone, right? And that's not what I'm looking for. All I'm just looking for is just to add 1 day, right? And it's changed the entire structure of what I've created itself, right? Now, this is where periods come in, right? Periods helps you solve problems like this, right? So periods are time spans, but they don't have that fixed length in terms of seconds, right? So in this case, it mentions that they work a lot more with human times, right? Because, I mean, it's a lot more interpretable. So in this case, if I'm working with a period, it's going to give me something that probably is a bit more intuitive, right? So if I do exactly the work that I did here, and I'm working with periods, so instead of the D days, all I have here is just days. I add just 1 day. It's going to give me what I'm looking for. The only thing I'm looking for to change is just the day component itself. It keeps the hours and every other thing the way it's supposed to be, right?
Doesn't it change the time zone again, though? Like
yes, it does.
Mm-hmm.
Yeah. So as soon as I get to the time zone, as soon as I get to the time zone bits, I think that's where this is going to be. This is like an entire topic on its own. for why this time zone always changes. Yeah. So like durations, period also comes with a number of friendly constructors. So I won't run through this because it's very similar to what duration has. The only difference is you just remove the D that's in front of each of these constructors, right? And it give you what you're looking for. And you can also do the same arithmetic journey here. I can multiply, I can also add, I can also subtract. All right. And like I said, compared to durations, they will likely give you what you are expecting, right? So in this case, I have a leap year. I'm trying to add a year. It's going to give me what I'm looking for. I create another one. I have 1 year. Like if I'm using durations, for example, it distorts my entire information here because all I'm trying to do is to add 1 year. So what I'm looking for to change is this 2016 to 2017. But you notice that under durations, it's keeping it the same way because, this is a leap year. So you just add in like 365 days, 366 days, right? But my period function does exactly what I'm aiming for. It allows me add that extra year, right? So it gives me 1st of January 2017 because I'm adding an extra year to 1st of January 2016, right? Then it does the same thing for my daylight savings, right? So the object I created, I add 1 day, does exactly the same thing. So duration would distort my entire information. Like I said earlier, period will keep it the way I want it to be, right? So he said, let's use periods to fix an oddity related to flight dates. Some planes appear to arrive at a destination before they actually depart from New York City, right? So I guess maybe the first place to do is if I decide to visualize the entire data itself, you notice that there are some negative arrival days here, and that's what this period tries to fix. And as soon as I get here, that's what this information tries to solve. So let me just go through the formula itself. All right. So this looks at my data set, tries to filter arrival times that are less than departure times. All right. You can see that there are some of them that are less than departure times itself. Right. So it says these are actually overnight flights. We use the same information. You use the same date information for both the departure and arrival times. But these flights arrive on the following day, right? So we can fix this by adding days to the arrival times of each overnight flight, right? And that's where this comes in, right? So the way I can fix this is I have my data sets, I mutate it to create new columns for me because now I realize that there are some flights that are overnight flights and I need to add an extra day. Now what I'm just doing is for my arrival time column, just add an extra day and I can multiply that overnight by 1. So I guess this tries to explain the entire arithmetic work I can do here, right? And why period is probably the best class for you to use, right? So like I said, interestingly, everything now obeys the laws of physics, right? So you notice now, so now it's asking, are there arrival times that are less than departure times? And the answer now is going to be 0 because now you have no such information. Otherwise, if you had come here, you had like 10,000 rows that had arrival time that are less than departure time, which is not supposed to be the case, right? So the final bit on arithmetic is now intervals, right? I think I'm 1 minute above time. I'll try to get this sorted out in like maximum 5 minutes. Intervals. So this is just talking about like the division function itself, right? So if I decide to divide D years, this should give me 365 days. By 365 days, it's obvious what I'm supposed to get. Because duration is always represented by number of seconds, a duration of a year is defined as 365 days worth of seconds. So what should this return, right? So I'm using period itself. Well, the period is not a leap year. It should return 365 days. But if it was still a leap year, it should return 366 days, right? There is not quite enough information for Lubridate to give you a clear answer on this. So what it does instead is it gives you an estimate, right? Even if I'm using periods, right? So if I do this, right? Again, like if the year is a leap year, it should give me 365 or give me 366, right? But it's not going to give me like a 1 in itself, right? So estimates only convert to intervals for accuracy, right? So in this case, it's giving you 365 days, right? So it's saying if you want more accurate measurement, you'd have to use an interval, right? So an interval is a duration with a starting point that makes it precise, so you can determine how long exactly this takes. So like if I create this object, I have today, and I add 1 year, right? And then I can do my today, I pass this through, next year, and I divide that by day. So this is trying for me to be a bit more accurate in information I'm aiming for, depending on the particular year that I'm in, either a leap year, a non-leap year, right? Then to find out how many periods fall in an interval, you need to use the interval integer division, right? Rather than just this straight line division, you need to use an integer division itself, and that gives you, the exact number, right? So I mean, I think this summary page just talks about most of the things that I've mentioned. Why you should look for, why you should use periods over duration, and why you should use intervals. So I mean, it tries to specify what you can do in between, but the major idea is always try to look for the simplest data structure that solves for what you are aiming for here, right? If you only care about physical time, use duration. If you care about time that should be interpretable, use a period. And if you need to figure out how long a span is in a set that is interpretable, which is what these human units try to use an interval, right? And it just gives like a summarized idea of like a framework for you to know what to choose depending on what you're doing, right? The final bit is time zones. So I'm just going to run through this itself. Everything this is trying to teach is, again, there are different time zones in like different geographical locations, right? To avoid confusion, R tries to use what is called an international standard IANA time zone, right? And the way it uses it is typically in the form of a continent and a city. However, one of the things I also try to teach you is the reason why it specifies a city is there are certain cities that also have different time zones, right, within a particular continent or a particular country, right? And an example would be New York and Detroit. They said both cities were using Eastern time zone, Eastern Standard Time in 1969-1972, but Michigan changed much later, so it means a different thing, right? And you can read an entire database of this to kind of figure out some of the problems that's happened with time zone itself, right? So like I said, if you want to find out what your current time zone is, you can use this argument itself. So sys.time zone, right? If R doesn't know, it's going to give you an NA. And if you want to see the complete list of all possible time zones, you can use OC names itself, right? And in R, the time zone is just an attribute of that datetime that only controls for printing. For example, this 3 object represents the same instant in time, right? They are the same instant in time, they're just different time zones itself. So depending on what your system information is, right? So this would be same time in America, same time in Copenhagen, same time in Auckland, right? I think that is about it. Otherwise, Lubridate also uses UTC. So this is one of the things I was trying to mention. So the Lubridate package specifies or uses UTC itself, but you can also determine to conform it to particular time zones by using T-zone itself.
So if you're inserting a time, it will automatically by default set it in UTC, but you can specify it and it can change, right?
Exactly. So the way you can change it is, so there are 2 ways you can change the time zone. So you can keep the instant in time the same and change how it's being displayed, right? So in this case, you can use the create an object with time zone. So this is the function that you pass X4. And I think we created X4 here. So this is the entire information set that we created for X4. They're now specifying a time zone. So I want Lord Howe in Australia for my time zone. Right. So it's going to create each of the component of X4 and benchmark it to that Australian time. Right. The other way is to change the underlying instant itself. Right. Instead of using which time zone, I can use force time zone. So with this, I can now force it to change my time zone itself. Right. And that's what this now looks like. Then I can also do my mathematical operations with that. So that's just the idea. I mean, your system could have a time zone, but you can also force feed whatever time zone you are correctly aiming for. All right. So I've tried to condense the entire lesson itself in an hour.
Yeah, you did a great job. It was very succinct and it went quite easily compared to other chapters. It was, I guess, it felt a bit smaller than the usual chapters.
Yes. So interestingly, I think we are moving into the next category of this chapter, of this book itself, so programs. I think this is one of the most interesting categories. So I think you are taking us in the next class, if I'm not wrong.
Yes.
Fantastic.
At the pipes with Margaret, and program is just a very, I think, rough introduction.
Yeah, no problem. All right. Thank you very much, Valeria. Thank you very much for listening.
Thank you, Daniel, so much for the wonderful presentation. So
it's fine. Thank you very much. Same to you. Cheers.
Bye.
Bye.